Okay, so I'll start this lecture. This is basically week two. Um, okay, sorry. So I'll start this lecture. This is week two, and I'm solving this week's assignment. Assignment two, right? Okay. So again, as usual, I'll not solve the whole question. I'll try to give you a flavor by solving one or two parts, and then you can follow up the rest by yourself. Okay. So what is the first question? The first question is, which of the following cannot represent the real part of an analytic function? Mark all statements that are true. So the question is, which of the following cannot represent the real part of an analytic function? And you have to mark all the statements that are true. Uh, so separately, so here we're not given any imaginary part, and separately we have to judge whether the real part is that of an analytic function or not. So how do we do that? So in the last week's lecture sets, we know that this can be done by checking whether the function u and v, they both should satisfy Laplace equation. That is what we know. So if some f of z is equal to, I'll zoom this in. If f of z is equal to some u of x comma y plus I p of x comma y. Okay. So if this is my complex number, complex function, actually not just complex number. If this is my complex function, then we know that both u and v should satisfy Laplace's equation. Basically, u and v should be a harmonic function, right? So that is all that we have to check here. So let's go ahead and do that. Um, so for u, this condition turns out to be del square u by del x square plus del square u by del y square is equal to 0. So this is all we have to check for all the four parts. Maybe I'll check for just the first part. For the first part, u of x comma y is equal to x square plus y square. So therefore, del u by del x is equal to 2x del square u by del x square is equal to 2. Similarly, del u by del y is equal to 2y, and del square u by del y square is equal to 2 again. So what I want is this equation to be satisfied. Del square u by del x square plus del square u by del y square is equal to 2 plus 2 is equal to 4, which is not equal to 0. Therefore, 1 cannot represent the real part of an analytic function because the function u given in 1 does not satisfy Laplace equation. So we can claim that 1 cannot represent the real part of an analytic function. I hope that's clear. Okay, so that was question 1. Now let's move on to the next question. Okay, so let's read the question very carefully here now. What does the question say? Just yeah. So what does the question say? Which of the following represents the derivative of a function f of z is equal to u plus iv at a point z0 is equal to x0 y0 or z0 is equal to r0 theta 0, depending on how we choose to represent uh, where it is analytic. So what we're saying is that we are assuming that u and v are analytic in a particular region, and what we want is we want to see which of the following functions are representing the derivative of this function at a point x0 y0 or r0 theta 0. Okay, so we have to mark all the correct answers. So this is basically representing the full expression of the derivative in terms of x y or r theta. Okay, so that's all you have to do. So for that, how do we proceed? What we can do is, let's go by the very basic definition of what f prime of z0 is. Okay, by the way, so sorry, I will give you an idea of I'll give you a flavor by solving option 3. Yeah, I'll just give solve option 3 to give you a flavor, because option 1 and 2 it's uh, with respect to these coordinates, x and y coordinates. So that is something that you can do. You'll be able to do easy in a much easier manner. But r and theta might be a little bit difficult. So let's try and attempt that. So if I'm doing the r part, you should be able to do the theta part as well. All right. So let's try and do this. Uh, what is f prime of z0 exactly? F prime of z0 is equal to basically sum f prime of z0 plus delta z. Sorry, it's f of z0 plus delta z minus f of z0 divided by delta z in the limit delta z tends to 0. In this limit is what we are looking after. Okay, so now because we are representing everything in terms of polar coordinates, delta z is equal to r e raised to the power of I theta, delta of this. So basically what I'm saying is that I'm representing z as r e raised to power I theta. Z is equal to r e raised to the power of I theta. So delta z is equal to delta of r e raised to the power of I theta. Okay. All right. Now what I want to do is, because third option clearly shows me that both the derivatives are with respect to r, the radial vector, the radius. So what I'll do is I'll say that delta z tends to 0 implies delta r tends to 0 and theta is constant. So I'll keep theta constant so that the del theta part does not come in anywhere. I just want the del r part. Okay. So basically I am approaching the point z0 in the radial direction. That's the idea behind this. Del r tends to 0, but theta is being constant. So I'm approaching that particular point in the radial direction. Okay. So then del z becomes e raised to power I theta into del r. Okay. And f of z0 plus delta z also becomes what? So f prime of z0 is equal to limit delta z tends to 0 u of, now I'm writing f in terms of u and v. So f is already, f is simply u plus iv, right? It's already given in the question. F is equal to f of z is equal to u plus iv, and this function is analytic. We have to assume that this function is analytic. So let's go ahead and solve this. U of, u is basically a function of r and theta both. So what are you doing here is r0 plus delta r comma theta plus I v r0 plus delta r comma theta 0, I'll say u of r0 theta 0 minus I v r0 theta 0, this whole divided by I'll divide this whole thing by delta z, which is delta r into e raised to power I theta. Okay, so now what we'll do is equal to u of r0 comma theta 0 plus delta r del u by del r. Right, what I'm doing is just simple Taylor expansion because this is an analytic function, so you can do this basically. Just a moment. All right. Um, so what does this lead to? This gives me e raised to power minus I theta. This e raised to power minus I theta I'm taking outside, delta r del u by del r. And similarly, if I do the same thing here also, so it gives me plus I delta r. I suppose the same thing will happen here also. It's not I suppose, I'm sure the same thing will happen here also. Del v by del r divided by delta r. So this becomes equal to f prime of z0 becomes equal to e raised to power minus I theta del u by del r plus I del v by del r. So this is what I end up getting. And what is the expression here? E raised to power minus I theta del u by del r plus I del v by del r. So yes, if I evaluate at some point say r0 theta 0, then this stands correct. So this is the correct option. In a similar manner, I can also solve the fourth part. Maybe I'll just give it a try so that uh, let's see if that's more difficult or it's simple. Okay, so from here, this is till here, this part is okay. Um, in this part is okay. I put it up like this, that f prime of z0 is still the same thing, limit delta z tends to 0, f of z0 plus delta z minus f of z0 divided by delta z. Z is r e raised to power I theta, um, and f is u plus iv. So, but now, yeah, also delta z is this. But now, delta z tends to 0 will imply that delta r is constant. Basically, delta theta tends to 0 and r goes to constant. All right. Mm, okay. Okay, so we're seeing that now we are slightly changing. So delta z would mean that we're keeping r as constant and we're slightly changing delta theta only. So what would delta z become? Delta z would become uh, delta of r is e raised to power I theta. R goes out common. Uh, e raised to power I theta remains as it is into I del theta is what will come out. I into del theta. Yes, this is what will come out. Okay. And then let's put it up here. F prime of z0 is equal to limit delta z tends to 0 u of r0 comma theta 0 plus del theta plus I v r0 comma theta 0 plus del theta minus u r0 theta 0 minus I v r0 theta 0 divided by r e raised to power I theta I del theta. Same thing. Again, we can go ahead and Taylor expand this, and the first term it will cancel this term. So what I end up getting is u of r0 comma theta 0 plus del theta is equal to u of r0 plus del u by del theta. So because that's the second variable into uh, delta theta. Okay, so doing this, what we eventually end up getting is delta theta into del u by del theta plus I delta theta del v by del theta divided by r e power I theta I d theta. So it is equal to 1 by z minus, sorry, it's minus I by z del u by del theta plus I del v by del theta. That's your final answer, f prime of z0. What's the option? Minus I by z0 del u by del theta plus I del v by del theta. So even this one's correct. This is what we are exactly ending up getting. So even the second option is correct. Okay. So this is just simply using basic, sorry, basic principles to find the derivative form. So for the first two parts, you can solve it yourself. I solved the third and the fourth part. The first two parts, now that I have shown this method, the first and second part should be relatively simple. Okay, so moving on. Okay, so now this is the third question. Which of the following functions is or are nowhere analytic? Mark all correct answers. Okay, so for nowhere analytic, we know the conditions for analyticity, the Cauchy-Riemann conditions. So let's see which of the functions are nowhere analytic. So for the first one, I'll maybe solve just the first and the third part. The rest you can solve yourself. The first one is xy plus iy. Right. So for this function, u is equal to xy, v is equal to just y. So applying the CR conditions, del u by del x is equal to del v by del y, del u by del y is equal to minus del v by del x. These are the Cauchy-Riemann conditions. So applying it in the first part, what we get is del u by del x. Del u by del x is just y, del u by del x is equal to y, del v by del y is equal to 1. So clearly here itself, del u by del x is not equal to del v by del y except at y equals 1. Okay, now let's use the next condition. Del u by del y is equal to x. Del v by del x is equal to 0. Okay, so what does this give me? Del u by del y, del v by del x. It tells me that del u by del y is not equal to del v by del x except at x equals 0. So what this tells us is that at x comma y corresponding to 0 comma 1 analytic function. Okay, so the idea is that you can see that at x comma y, the Cauchy-Riemann conditions are being satisfied. But when we define analytic function, we always mention that the function should be differentiable. So CR conditions give you mainly differentiable. But for an analytic function, there is an additional requirement that the if we are saying that it's analytic at a particular point x0 comma y0, then the function should be analytic and differentiable in a small region around that point, not at just that point. So here clearly CR conditions are satisfied exactly at 0 comma 1 only, but nowhere else. So in this case we cannot call this an analytic function because it's differentiable, possibly differentiable only at just one point. So that is why this is not an analytic function. Why? Because it satisfies CR only at one point. and no such neighborhood. So it's not an analytic function. Okay, let's move on to the next one. Okay, maybe I was solving this one itself. What about the other part? Maybe let's solve third part now. E power y into e raised to 1 minus ix. This is the function. So first we'll have to split it into u and v, the real and imaginary part. So e raised to power y can stay outside. E raised to power minus ix is cos x minus I sin x. It's cos x minus I sin x, right? So here I have to check the CR conditions. U becomes equal to e raised to power y cos of x, and v becomes equal to e raised to power y minus e raised to power y into sine of x. This is my u and v functions. So to satisfy Cauchy-Riemann, we'll have to check the partial derivatives. Del u by del x is equal to minus e raised to power y sine x. Del v by del y is equal to minus e raised to power y sine x. We can see that both of these are equal. Minus e raised to power y sine x. Let's check the next one. Del u by del y is equal to e power y cos x. Del v by del x is equal to minus e raised to power y cos x. Therefore, del u by del y is equal to minus del v by del y. It is the negative counterpart, right? So basically, CR conditions satisfied everywhere. Therefore, function is analytic. So we check the first one and the third one, and both. Sorry, the first one was nowhere analytic, but the third one was everywhere analytic. So what we want is we want functions which are nowhere analytic. So this is the correct answer, and this is the wrong answer. It is analytic. But what we want is a function which is not analytic. So that's why the third one is the incorrect answer. Okay. So now the next one is which of the following functions is or are entire? So entire functions, what are entire functions basically? Entire functions are analytic in the entire complex plane. They are analytic everywhere basically. So now to comment whether the function is entire or not, we have to check its analyticity and ensure that the analyticity is true for all possible values of x, all possible values of x and y, right? So that's what we want to check. Which of the following functions is or are entire? Let's start with the first one. So this is the function 3x plus y plus I into 3y minus x. Um, so to check whether it's entire or not, obviously I'll uh, try to evaluate the Cauchy-Riemann conditions, CR conditions. I'll see whether it's being fulfilled or not. U is equal to 3x plus y. V is equal to 3y minus x. Therefore, del u by del x is equal to 3, del v by del y is also equal to 3. So here it's trivially satisfied. Del u by del y is equal to 1, del v by del x is equal to minus 1. Therefore, even this second condition is being trivially satisfied. So at no point in the complex plane can these conditions not be satisfied. Cauchy-Riemann conditions for this function will always be satisfied in the entire complex plane. So that is why this function, the first one that we've chosen to look at, is analytic. Okay. Um, let's check the second one maybe. Sin x cos y. Okay, so this is my function. U part is clearly defined. It's sin x into cos y plus, no, this is the u part. The v part is cos x into sin h y. So now we'll go forward and evaluate the Cauchy-Riemann conditions for these functions. So del u by del x is equal to cos y into cos x. Del v by del y is equal to cos x into cos y. Okay. So therefore the first Cauchy-Riemann condition is already satisfied. Let's look at the second one. Del u by del y okay cos x into sin h y. Cos x into sin hy. Mm, and here it's Sin x into sin hy dv by dx is equal to minus I sin x into sin hy. So even the second condition is satisfied. Second CR condition is also satisfied, right? So what do we end up getting is that CR conditions. It's an analytic and it's an entire function because CR conditions are being satisfied everywhere. So the first and second one both are analytic and entire. Here also, of course, this function is entire. This was question 4. Now let's move on to question 5. Okay, so suppose V and capital V are harmonic conjugates of U in some domain. There are two harmonic conjugates that they're talking about, and yeah, which of the following statements is true? V and V and capital V are harmonic conjugates of U. Which of the following statements are true? V and capital V can differ at most by an additive constant. That's one of the statements. And there is can differ at most by multiplicative constant. One is saying that both have to be equal, and the fourth one is that they may be completely different. These are the four options that we have. So let's write two analytic functions. Okay, so two analytic functions. One is u plus iv. Second one is equal to u plus I into capital V. So because uh, we've been told that u and v are harmonic conjugates of each other and they are analytic, of course, as well. So f1 and f2 both are analytic functions in some domain. Now we know that when we have two analytic functions, we can add them up. We can have a linear combination of these functions, and even that's an analytic function. So f1 minus f2 should also be analytic. This comes from the properties of analytic functions, right? So f1 minus f2 has to be analytic. Therefore, f is equal to f1 minus f2 is equal to u plus iv minus of u plus I capital V. That gives me I into small v minus capital V. This is my new function f. For this function to be analytic now, for this function to be analytic, v minus capital V has to be a constant. Why? Because if you think about Cauchy-Riemann conditions, for this function, there is only imaginary part, there is no real part. So del u by del x and del u by del y, both are zero. But on the right hand side, they are non-zero. If v minus capital V is not a constant, then on the right hand side, as in the derivatives corresponding to v are can be non-zero at any particular point. So basically, they cannot be a function of x or y either. What I'm trying to say, let me just write it down. Del u by del x is equal to 0. Del u by del y is equal to 0. For this function I'm talking about, by the way, I'm talking about f, which is u plus iv. U corresponds to 0. V corresponds to I into small v minus capital V. So del u by del x is equal to 0. Del u by del y is equal to 0. Um, so these are both 0. But del v by del x and del v by del y, it will be some function of small v comma capital small v and capital V. Let's call this u0 plus iv0. V0 is this, u0 is this, right? V0, v0. So when I'm taking this derivative, it will depend on small v comma small v and capital V, unless small v minus capital V is always a constant. In that case, I can assuredly say that these also come out to be 0. 0 by del x is equal to del v0 by del y is equal to 0. So therefore, it proves that small v minus capital V has to be a constant for for of course this function to be analytic everywhere. This has to be a constant. All right. So that is my question 5. Now let's move on to the next question, question 6. Let the function f of z is u plus iv be analytic in some domain. Let us define the functions capital U is equal to e raised to power u of x comma y cos v x comma y, and capital V as some e raised to power u x comma y sin v of x comma y. Okay, and they're saying that u and v basically are analytic in some domain. So which of the following statements about the function g of z, which is capital U plus I into capital V, is true? Okay, so what are the statements? The statements are that g of z is always non-analytic in the given domain. The combined function g of z is always non-analytic in the given domain. Second statement is g of z is analytic in the given domain only if v of x comma y plus I u x comma y is also analytic in the given domain. Third option is that g of z is analytic if u and v are constants. Fourth one is g of z is always analytic in the given domain. There are four options to consider. Okay, but let's do what we do best directly. G of z is equal to capital U plus I capital V. Capital U is equal to e raised to power u of x comma y cos v x comma y. Right? Therefore, del u by del x So to e raised to power u of x comma y into del u by del x into cos of v of x comma y plus plus uh, e raised to power u of x comma y, um, del of cos v of x comma y, right? So that gives me into sine with a negative sign here minus sine of v of x comma y into del v by del x. Is there a doubt, Sanjeev? Okay. All right. All right. Okay. Now del v by del y. So for that, I'll also have to write v. V is equal to e raised to power u of x comma y sine v of x comma y. So del v by del y simply gives me uh, e raised to power u of x comma y del, this is capital V, del u by del y. And there's a plus sign here. I have to take the derivative with respect to y. So into sine v of x comma y plus e raised to power u of x comma y cos v x comma y del v by del y. All right, so this is what the derivative looks like. Okay, so now for satisfying Cauchy-Riemann conditions, capital del of capital U by del x has to be equal to del capital V by del y. Therefore, e raised to power u x comma y cos v x comma y del u by del x sine cos. What I'm doing is actually del u by del x minus del capital V by del y. That is this is equal to this comes out. So del u by del x minus del v by del y is what I'll get. This del u by del x, which is As it is for u x comma y sine v x comma y into del v by del x. Del y sine of v of x comma y, which is equivalent to um, del u by del x has a negative sign, and del v by del y does not have a negative sign, but when I shift it to the left, it does acquire a negative sign. So this is what it is. I'm evaluating this again. So because there is a negative sign in front of del v by del y, capital V, del capital V by del y, so that's why there will be a negative sign here also. And if I simply, because u and v are both analytic functions, basically f of z is an analytic function. If I simply use CR conditions on small u and small v, then in that case, this becomes 0 and this becomes 0. Both of them will become 0. And what I'll end up with is del u by del x is indeed equal to del v by del y. So similarly, you can do the second part like this. All right. So as in, what do I mean by second part? So I have just seen one equation, one Cauchy-Riemann condition, and I have shown that uh, it indeed satisfies the first Cauchy-Riemann condition. Now check for del u by del y is equal to negative of del v by del x. Check out for this condition in this problem itself, and then you can answer confidently whether it's analytic or it's non-analytic, whatever. So I don't want to solve the whole question because that's not the purpose of this tutorial. So I'm not solving the whole thing, but uh, one part at least gives you a flavor of how to approach this. So you can do the second part and get the answer finally. Okay, so f of this is f of x comma y is equal to some real part of e raised to power 1 by z, and g of x comma y is equal to some imaginary part of e raised to power 1 by z. This is what we are seeing. These are the functions written explicitly in terms of x and y. No, we are supposed to write it in terms of x and y. Considering any domain which does not contain the origin, which of the following statements is true? And they've asked some statements regarding the harmonicity of these functions. So let's first write down in terms of x and y. So f of x comma y equal to real part of e raised to power. So now I normalize this and split it into real and imaginary. That's what I want to do because I want to just take the real part. F of x comma y is just the real part of this function, right? So maybe let's do this. Let's not put the real part first. Let's just see what this function gives us, right? E raised to power 1 by z is equal to this, is equal to this. So e raised to power x divided by x square plus y square multiplied by e raised to power minus I y divided by x square plus y square is equal to e raised to power x divided by square plus y square, and e raised to power minus I y I can write in terms of, say, cos and sine, minus, sorry, plus cos y divided by x square plus y square. This will be minus sin minus I sin y divided by x square plus y square. Alright, so basically f of x comma y is simply equal to e raised to power x divided by x square plus y square into 1 plus into simply cos of y plus x y divided by x square plus y square, and g of x comma y is equal to minus sine, sorry, the exponential outside, minus e raised to power x x square plus y square sine y divided by x square plus y square. That is my f and g. Okay, so now what I have to prove is that consider any domain which does not contain the origin and prove the statements whether it's harmonic or not. So to prove harmonicity, we know that we just have to make it satisfy Laplace's equation. We need to check whether the function satisfies Laplace equation. So del square f by del x square plus del square f by del y square. So del square f by del x square, how do we do that? We simply brute force differentiation, e raised to power x divided by x square plus y square multiplied by minus x divided by x square plus y square the whole square into 2x, right? Cos y upon x square plus y square, uh, plus, again the derivative will be for the exponential only, e raised to power x divided by x square plus y square multiplied by 1 divided by, this is just going to be, um, I'm taking the derivative of this, so 1 divided by x square plus y square. So both of these multiplied by cos y divided by x square plus y square. So this is the first derivative, right? Yeah. Did you say something, Sanjeev? No doubt. Okay. Del f by del x is equal to this. So this is the first term. I have to also differentiate the second term plus e raised to power x divided by x square plus y square into minus sine of y divided by x square plus y square multiplied by minus y divided by x square plus y square the whole square. I hope I've done this differentiation correctly. E power x divided by x square plus y square into 1 divided by x square plus y square. Yeah, right. Into 2x here. Yes. Yes, yes, yes. This is what the derivative will look like. If I take the second derivative now, I'll have lot of terms. Del square f by del x square is equal to, so now it's the second derivative del square f by del x square is what I need to evaluate, and this is just simply tedious. There is no conceptual thing here. You just have to brute force do it. So minus 2x square. Okay. Maybe before that, I'll just simplify this a little bit so it looks more decent, clean. Minus 2x square divided by x square plus y square, the whole square, into e raised to power of x divided by x square plus y square into cos y upon x square plus y square plus e raised to power x square plus y square into divided by cos. Plus e raised to power x divided by x square into sin y upon x square plus square. Okay, so this is just the simplified version of the first derivative. Now we have to evaluate the second derivative of f only. So minus 4x over by x square plus y square, the whole square is to power x square cos y divided by x square plus y square. The first term. So this is minus 2 power already, so there will be minus 2 here, and square plus y square, the whole cube is to power x divided by x square plus y square cos y divided by x square plus y square. So these are the two terms. Now the exponential term will differentiate, which is minus 2x square on x square plus y square, the whole square, to e raised to power x divided by x square plus y square into 1 by x square plus y square cos x square plus y square. Okay, so the second term is all differentiated. Let's do the first term as well. Plus minus 2x square divided by square plus y square whole square e raised to power x divided by x square plus y square. Are these? No. So I have to take x for x upon x square plus y square minus x upon x square plus y square. And cos y is here. What's here? We can see that. Okay, so this term e power x. mm, This is okay. This is in multiplication. This is just one term, right? Getting a little bit confused with all the. All right. So 1 upon x square is y square. This one is already done. This is the second part that we just finished. And now go for the third part. So now there will be a derivative with respect to cos y, right? It's 2x square upon square plus y square, the whole square raised to power x divided by x square plus y square minus x divided by x square y square whole square into, because this is a x derivative, so I can simply have minus minus sine y divided by x square plus y square. So this is again just one term. All right. So this is what we end up with. And this is just this one term. So now doing that all over again for the next one too. So basically there will be a lot of these kinds of terms. Uh, so just one, I have to write down these terms too and this entire term. So, so this is okay. 961. All right, all right. So basically what I did was I just finished the first entire term. All right. So the next one, this term, e power x divided by x square plus y square. It's got x derivative over x square plus y square into 1 divided by x square plus y square. Hence x divided by x square plus y square the whole square into this is just okay, into 1 by x square plus y square. Here there is one more term. X square plus y square plus e raised to power 4 x square plus y square minus 1 divided by x square plus y square the whole square into 2x cos y divided by x square plus y square. So this is plus e power x divided by x square. Mhm. Multiplied by 1 upon x square plus y square Actually, this whole square. Let's go into cos, so which becomes minus sine. Minus sine y upon x square plus y square into uh, minus y divided by x square plus y square. So this is again till here we only validated two terms. There is at least one more term here to evaluate. Um, e power x upon x square plus y square into sine of y upon x square plus y square into so these minus signs can be accommodated 2xy into 2xy. I'm removing this minus sign into 2x x square plus y square the whole square. So I differentiated the first term and minus of sine y. Though this remains the same, that's okay. Only x derivative. Right. So this is exactly that minus 2xy minus 2xy upon x plus y square the whole. That's it. Minus signs gets cancelled. Sign remains the same. It's 2xy. This thing. All right. Plus e to the power x divided by x square plus y square. Hmm. It's a long term. It's actually getting very confusing. I need to do it much more systematically. Okay, minus 1 upon the whole square into 2x minus sine y divided by x square plus y square to 2xy divided by x y square the whole square. Nice and you plus e raised to power x upon x square plus y square. This now remains the same. Minus sign becomes minus cos of y divided by x square plus y square multiplied by minus 1 divided by x square y square the whole square to 2x plus e raised to power x plus y square. So I differentiated this sine term. Now it's the time for 2xy term. So it's 1 upon x square plus y square sine y upon x square plus y square into 2y divided by x square, so y square the whole square plus e raised to power x divided by x square plus y square 1 divided by x square plus y square minus sine y upon x square plus y square into 2xy, the minus sign goes away, into 2 divided by x square plus y square whole cube. So this is the size of the term that we obtain for the second derivative. And you're supposed to do the same for second derivative with respect to y as well. So what we did is just second derivative with respect to x. So you have to take the second derivative with respect to y and then check whether it can go to 0 or not. So I know it sounds very tedious and very tough, but you will be able to map very similar terms. Once you do the second derivative with respect to y, you'll be able to see very similar terms, and you can see that the structure emerges that maybe adding that can give you 0. So, so next up was evaluation of del square f by del y square. I'm not doing this now because it will take a lot of time, and that's what we don't have right now. But my point being that this is just tedious, but there is no complication as such, as in there is no subtle mathematics involved here. It's just brute force method, right? So, but you'll have to go through the grind. So to check whether it's harmonic or not, you will have to go through the grind. There is no other way, no other option. So similarly, you also have to check whether g of x comma y is harmonic or not. So yeah, this is the only way I can think of, that you will have to differentiate it twice and then you'll have to equate it. So do this and then equate, and whatever you get is the answer. Yeah, all right. Let's move on to the next one. Okay, now which of the following statements is or are true? First statement is, let's check the first statement, log of 1 plus I the whole square is equal to 2 log 1 plus I, something of this sort. Is this statement true or not? So normally for logarithm, you know that these properties exist. Sorry. Normally for logarithm, you know that these properties are true. But generally, it's not necessary that these are true. Just give me a moment. I have to take this. Hello. हाँ 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 ठीक है ठीक है मैं एक्चुअली लेक्चर चल रहा है हाँ all right so yeah uh, here log of 1 plus I the whole square is equal to 2 into log of 1 plus I. So normally for logarithm we know that these kinds of properties exist, like suppose there is log of 3 square can simply be 2 log 3. You know that you can do this normally, but this is for real numbers. We don't know whether the same property exists for complex numbers as well. So we need to verify whether this property is true or not, right? So what we'll do is, let's write 1 plus I the whole square as 1 minus 1 plus 2I. So basically log of 1 plus I the whole square is equal to log of 2I. And what is this equal to? Uh, log of 2 e raised to power I pi by 2. So this is equal to log 2 plus I pi by 2. This is my LHS. LHS is equal to this. Now let's check what RHS is. RHS is equal to 2 log of 1 plus I is equal to 2 log uh, what is 1 plus I? 1 plus I is root to 2 e raised to power I pi by 4, right? Because e raised to power I pi by 4 is equal to 1 by root 2 plus I by root 2. So if I take multiply this by root 2 e raised to power I pi by 4, this becomes 1 plus I. So that's what I've done. 1 plus I have written as root 2 e power I pi by 4, right? So this is equal to 2 log root 2 plus 2 into I pi by 4. 2 log root 2, this you know that because now root 2 is a real number, so 2 then 2 into log of some number is basically log of the number squared simply. So it's basically log root 2 squared plus I pi by 2 is equal to log 2 plus I pi by 2. This is my RHS. So clearly LHS equals RHS. So that's why first statement is correct, right? I hope there is no question here. And similarly, you can solve the right. Okay. And similarly, you can solve the other parts as well. Um, should I solve any other part? First and fourth part look very similar. Log of I cube is equal to 3 log I. Again, even that looks very similar. Log of 11 minus 3I. Uh, that I'm not very sure. Let's try that then. Let's try the third one. Is equal to log of 2 plus 3I plus log of 1 minus 3I. Log of 2 plus 3I plus log of 1 minus 3I. Okay, so for the LHS, log of 11 minus 3i is equal to log 11. Actually, let's do this. What's the magnitude of this complex number? Let z is a complex number which is 11 minus 3i. So then mod z is equal to square root of 121 plus 9 is equal to square root of 130. Okay. All right. So this is simply log of square root of 130 raised to power I theta, some theta, where tan theta is equal to minus 3i, sorry, minus 3 by 11. So is equal to log root 130 plus I theta, or maybe you can say I of tan inverse minus 3 by 11. That's my LHS. What about RHS? RHS is equal to log of 2 plus 3i plus log of 1 minus 3i. When two logarithms, acha, but we don't know that. So normally when two logarithms are in addition, we can simply multiply their contents, right? But here in this case, we can't because we are again it's a complex number, so we don't know with what properties can work. Is equal to log of 2 plus 3i, so 4 plus 9 square root of 13 it is to power I theta 1, where theta 1 is I'll define that, plus for this complex number it's log square root 10 e raised to power I theta 2. So where theta 1 is equal to tan inverse 3 by 2, theta 2 is equal to tan inverse minus 3 by 1. Okay, so is equal to log root 13 plus I theta 1 plus log root 10 plus I theta 2. Therefore, log square root of 130 is something I already get, plus I tan inverse 3 by 2 plus tan inverse minus 3 by 1, minus 3 basically. So these are the two values here. Uh, and how to evaluate this? Uh, Tan inverse A plus tan inverse B. So we have a formula for tan of A plus B. Does anyone remember the expression? What is tan of A plus B? Tan A plus tan B divided by 1 minus tan A tan B. Of course. So is equal to log square root of 130 plus I into tan inverse tan A plus tan B, which is 3 by 2 minus 3 divided by 1 minus tan A tan B, which is 9 by 2. So this is like this is equal to log square root 130 plus I into tan inverse minus 3 by 2 divided by 11 by 2 is equal to log square root 130 plus I tan inverse minus 3 by 11, which is exactly this, right? This is what we end up with. So therefore, LHS is equal to RHS, and uh, this one is also correct. All right. So moving on to the next one, we've got two more questions to go. 1 plus tan square z is equal to sec squared z. So again, the question is which of the following statements is or are true for all z. So we have to establish these identities basically for any value of z. So let z is equal to x plus iy, and we want to establish whether 1 plus tan square z is equal to sec square z, right? So 1 plus tan square z is sine square z divided by cos square z. So you might again be tempted to simply cross multiply, say cos square z plus sine square z is equal to 1, and that is 1 by cos square z remaining. So that gives me sec square z. But again, sine square z plus cos square z being equal to 1 is not an identity we know for complex numbers. We have for sure proven it for real numbers. It is true for complex numbers, by the way, but here we are assuming that we don't know that, and we are out to prove it from very basic fundamentals. Okay, so this will 1 plus sine square z is e raised to power iz. So what is sine z is equal to e power I z minus e power minus I z divided by 2i. Is it? Cos z plus I sin z. Cos z minus I sin z. Yes. 1 minus I z divided by 2i the whole square divided by e power I z plus e power minus I z divided by 2 whole square. Minus 2. So this becomes what? 1 plus cos 2z minus 2 divided by 4 So 2 plus cos 2z minus cos 2z plus 2. I am making some mistake. Divided by cos 2z plus 2. So cos 2z is 2 sine squared z minus 2 sine squared z plus 1, and there is 4 on the. I think I made some mistakes somewhere. Let me check this again. This is 1 plus tan square z, which is sine square z plus cos divided by cos square z. अच्छा, so maybe should I? Hmm, mhm. Check this again. I made some mistake here. Okay, so this is 1 plus e raised to power 2 pi z plus e raised to power minus 2 pi z minus 2 divided by e raised to power 2 i z plus e raised to power minus 2 i z plus 2, and there is minus 4 here in the denominator, and there is 4 here, so there is only one minus sign remaining. What I'll get here is just one minus sign. All right, so now let's do this cross multiplication and see what we get. When I cross multiply, um, e raised to power 2 i z plus e raised to power minus 2 i z uh, plus 2 minus e raised to power 2 i z minus e raised to power minus 2 i z minus minus plus plus 2. So this gets cancelled. Of course, divided by the denominator is just e raised to power I z plus e raised to power minus I z, the whole square. So is equal to 4 divided by e raised to power I z plus e raised to power minus iz the whole square. So is equal to 2 divided by e raised to power iz is e raised to power minus iz the whole square. This is exactly the form that we're getting. And e raised to power iz plus e raised to power minus iz by 2 we know is cos z. So this is equal to 1 by cos z the whole square is equal to sec squared z. Hence proved. So this is how you will have to prove each and every identity here. Like uh, putting some form of z or doing these kinds of manipulations from scratch. You cannot assume these identities by default because they're applicable for real numbers. You can't just simply extend them to complex numbers. You at some point have to prove it, and this is exactly an exercise to prove that only. So yes, you can do the others in a similar manner. So for sine h, you know that it will. mm, so the next question has sine of h and some z, z plus pi I whatever. So for this, you know that sine h z is equal to e power z plus e raised to power minus z, sorry, minus e power minus z divided by 2. This is what sine h of z means. So basically use these basic identities to try and prove all these four parts and see whether the identities hold true or not. Okay, so that's the purpose of this question. Moving on to the next one. This is pretty straightforward. So what's the find the principal value of I raised to power I. Um, so I raised to power I. Firstly, I we know that is e raised to power I pi by 2, right? I can write I as e raised to power I pi by 2. So what is I raised to power I? That is simply equal to e raised to power I pi by 2 raised to I, which is e raised to power I square pi by 2 is equal to e raised to power minus pi by 2. So this is my principal value. So I've directly solved the last one. So yeah, this was the assignment, and of course I have not solved one part because it was very tedious and lengthy, and we don't have time to finish it. But the idea is simply just brute force because what you need to do is show that it's a harmonic function or not. So there is nothing else to do or think. Just brute force. Try to value the second derivative of uh, f with respect to x. Then try to value the second derivative of f with respect to y, and try to do it in a more organized manner. I think I did not do it in a very well organized manner. So try to do it in a more neater fashion, and you should be able to see whether adding the terms gives you zero or not, because very similar terms will emerge in both the cases. So that one part I did not do, but I still gave an idea of how to proceed about how to go about doing it. So that's it. That's our second assignment of second week. And if there are any more doubts, you can ask me, or else we're done with the session. Are there any doubts? No? Okay. All right. Thank you for joining, and bye.